Okay, so let's continue with the causal ordering of messages. So this is the third algorithm. So previously we saw the BSS algorithm and the SES algorithm. So again, a brief review of what is causal ordering of messages. So in this example, you can see message M1 was sent before M2, and M2 is received at P2, and after that P2 sends message M3 to P3. So the sending of M1 basically happened before the sending of M3. So the delivery of M1 should happen before the delivery of M3. So that's what is meant by causal ordering of messages. So we have algorithms to look at the or to facilitate causal ordering um, based on different ideas. So we saw the BSS algorithm that was a broadcast based. So when a process wants to send a message to a specific process, it still ends up broadcasting to all processes. And then the SES algorithm, which is strictly unicast based. But the trade-off is you have more information to be sent as part of each message to indicate the receiving process what messages were sent to it prior to this message. And now we are going to see at a more generic algorithm, the matrix algorithm, which can be used for unicast broadcast as well as to send to a specific group of processes, which we call as multicast. So the matrix algorithm is essentially storing information about the messages that were sent from one process to all processes, and the messages that were received at a process from every other process. So we have a matrix that is essentially captures information like this. So a row I indicates the messages, the number of messages that were sent by process PI to others, and the column I indicates the number of messages that were received by PI from the other specific processes. So this algorithm is almost like the BSS algorithm, it is broadcast based. So we increment the matrix entries only for the sending operation. There's no need to increment for the receiving operation because we keep track of the number of messages we have received in the columns. So let's look at an example, and that will be easy to understand how this algorithm works. So we have here three processes. So to start with, the entries for all the processes is an empty clock like this with all zeros in the matrix entries. And now P1 is sending a message to P2. So as I just said, if you want to keep track of sending, you increment in the row for that particular process. So P1, so that's row 1, is sending a message to process 2. So in the second column, we increment from 0 to 1. So that's the basically here you don't have a vector clock, you have a matrix clock at each process. So you send this matrix also as a timestamp for this message, and after sending that message you send another message. Now that message is sent to P3. So P1 is sending a message to P3. So in row 1 you increment the third column from 0 to 1 and you send that. So this is your matrix clock. Now send that time message, the message with this timestamp to P3. Now P3, it's initially it is having a clock, matrix clock like this. So when you compare the clocks, so P3's matrix clock is something like this to start with. So when you look at this, the third column, because this is at P3, the third column indicates the number of messages you have received from every other process. So what P1 says is this, so, or this basically the clock of the message. So what P1 says is, I know that you have got 0 messages from P2 and 0 messages from P3 itself, of course, and then this is 1. So essentially there's nothing been sent prior to this message. So if you compare these two columns, the rest of the rows are the same except this, which is basically indicating that this is a message sent by P1. So P3 can go ahead and accept this message, and you do a component wise maximum of these two matrices. Nothing is going to change except for this entry basically. Alright, so now when P3 sends a message to P2, P3 sending, so this is third row, and to P2, so increment the second column from 0 to a 1. So you send this to P2. So this is the matrix clock at P3, and this is the timestamp of that message. Now P2 needs to decide whether to accept that message or not. Now P2 looks in the second column because that gives the number of messages you have received from the other processes. And if you look at the timestamp, it says that, so this is actually the matrix clock at P2, and this is the timestamp of the message. It says that P3 has sent a message, which is of course this message, but P1 has sent a message to P2, but the current matrix clock at P2 says basically the second column, nothing is received from P1. So P2 has to essentially wait for that message that is being sent by P1. So when this message with this timestamp comes to P2, looks at this column, and only this column is 1, this entry is a 1, so that indicates that this is this message sent by P1. So P2 goes ahead and accepts this message and do as a component wise maximum of this one with this, so it gets this essentially. So now when it compares this column with this, essentially the this is the only one that is larger than this 0, everything is the same. So and this is because P3 is sending this message, so this message which was buffered earlier can be now delivered to P2. So that's the way the causal ordering is guaranteed for the messages. Okay. Okay. So another example. So here we have P3 is a broadcast here. So the previous example was for unicast, and this is for broadcast. So P3 is sending a message to P1 and P2. So P3 is incrementing this entry to a 1 to P1 and this entry to P2, and is sending this clock value, the matrix clock, to on both these messages. And after receiving this message, now P2 can accept this message because in P2's column this is the only thing that is 1, so it can go ahead and accept it, and that becomes the clock value for P2 actually. And now when P2 sends a message to P1 and P3, so essentially updating this clock, P2 increments its entry to P1 a 1 and P3 a 1, so it sends that clock value to these guys. And now when P3 gets this with this clock value, of course P3 as this looks at this and comparing to this, this is the only entry where it is greater, and that corresponds to this message, so P3 can go ahead and accept this. Whereas when you look at this P1, when P1 sees this and he looks at this column for 1, it indicates that, of course, this one indicates this message is being sent, but this one indicates that P3 has sent something to P1. So, and P1 has not received it because its clock value initially to start with is going to be all zeros. So when P1 looks at its clock value and compares with this timestamp, this is going to indicate that P3 has sent something to P1 and P1 has not received it. So when P1 gets this with this timestamp, of course now P1 can go ahead and accept this, and when it looks at now this timestamp again, P1 has got that message from P3, so P1 can now accept this message coming from P2. So it buffers that message. So now when you look at the analysis of this algorithm, you have the n processes, and each process needs to maintain a matrix now. So it's a tight bound n rows and n columns, so that is state of n square. And the message size is so you have again a matrix sent as a part of the timestamp of a message, so it's again theta of n square. And the number of messages sent per communication, it depends on whether you're doing unicasting or broadcasting. If you're doing unicasting, you send only a message to that process, like in the first example. Whereas in the second example, if you're broadcasting, you send message to all processes. So that is state of 1 if you do unicast and theta of n if you do broadcast. Now the clock increment operation compared in all three algorithms. In the BSS and the matrix algorithm that we just saw, we are keeping track of essentially doing broadcasting in both cases. In the BSS algorithm, we are broadcasting directly, so we keep track of the number of messages we have sent. So when a process receives a message with a particular timestamp, that timestamp indicates the number of messages that have been broadcast by the sender process to all the other processes, right? Of course, it has the other information too, the number of messages that have been broadcast by the other processes, okay, that the sender process comes to know. So, so essentially, that indicates what all have been sent so far in the system. So when a particular process is trying to send something, so let me just trying to illustrate here. So when I get a message and it has some, so this is the process P2, and let's say it has some clock value, say 3, 4, 2, and say 3. So that essentially indicates the number of messages that were broadcast by process 1, process 3, process 4. Of course, P2 knows about itself. So anything that is now sent by P2 to others. So when P3 is receiving this process, right? Or this message, and P3 is receiving this message. Of course, P2 is going to increment its clock values, so it's going to send 3, 5, 2, 3. So that's going to be also the timestamp of this message. So what it should be is P3 should have received all those 3 messages from P1. P3 should have received all those 4 messages prior to this message from P2, and all those 3 messages from P4, because the sending of this particular message happened after all those messages were sent by the other processes. So you sent 3 messages from P1, and you got to know about this from whoever sent it, and you send this message after this. So all those messages, the sending of those messages happened before the sending of this message. So which means P3 should have received all those messages prior to this. So you increment only for sending a message, and since you're doing broadcasting, you are capturing that information when you broadcast the timestamp of the messages that indicate the number of messages you have sent from a process to every other process. In the BSS algorithm, sorry, not that's what's in the BSS algorithm. In the matrix algorithm, you essentially keep track of the number of messages you have sent to every process, and if you look at from the column wise, that indicates the number of messages you have received from the other processes. So again, when you send that information only as a unique as message here, but still you are essentially conveying what you know about the messages sent by the other processes to you. So like in this case, when you send this matrix to P2, you are conveying through the second column what you know about the messages that were sent to P2, and you are telling that P1 has sent this message to P2, right? One message to P2, and P2 has not received that message yet. When you are trying to deliver the message here, P2 has not received anything so far. So that makes P2 to essentially think that it has to wait for this message to be, or basically it has to buffer this message and wait for this message that was sent by P1 to be delivered, because this message, this particular message was sent after you came to know that P1 has sent something to P2, because you got to know this based on a message that was received by P1, this message. So since this message, the sending of this message happened before this message was sent, then the receiving of this message should also happen before the receiving of this message. That's causal ordering of messages, right? So that's why it is, in this case, in the matrix algorithm, the columns keep track of the messages that you should have received from the other processes. So that's why you primarily increment in the row wise when you're sending some messages, and you don't do any updates when you are trying to receive a message. Whereas in the SES algorithm, which is unicast based, you are trying to increment a message, the clock value, when you receive a message. And that's because after you receive a message, like in this case, after you receive a message from this process, you are sending another message to say this to P2. So P2 has to know what messages that were sent by some other process has been received by you, and then after receiving all those messages, you are sending this current message. So that's why you have to increment the clock value for receiving also an SES algorithm, because you have to kind of capture the events that you have, that indicates that you have received some messages that were sent by the other processes, and after receiving those messages, you are sending this message to P2, right? So that's why you have to increment the clock for receiving also, in addition to sending, when you do the SES algorithm.